In this series of videos, we're going to examine sequences. And a sequence is a set of numbers in a particular order. There are various ways to express them, but one would be, for instance, a sub n is equal to 2 plus negative 1 to the n divided by n. In the exercises we're going to see in this section, I'll bring the theory in as we need through the examples. So let's jump into this one. The first 10 terms of this sequence are generated using a calculator, and notationally we use curly brace a sub n and then a little foot script n equals 1 and then a subscript 10. Kind of like limits of integration. And calculator values for the first 10 terms are 1, 2.5, 1.6667, 2.25, 1.8, 2.1667, 1.8571, 2.125, 1.8889, and 2.1. These are rounded to 4 decimal places where appropriate. Let's see what these look like as plotted on a graph. Here they are. I have my n-axis, and for n equals 1, my value is 1. N equals 2, my value is 2.5, and so on. And right now, the point of plotting these on the graph is to see if it looks like there's a trend. Does it see that they're trying to become one number in particular as n increases? And it looks like the answer is yes. This idea is the idea of a limit. We're going to make a guess here that the limit as n approaches infinity of 2 plus negative 1 to the n over n is equal to 2. Now, math kind of starts with guesses, but that's not where it ends, right? We have to do some proof sometimes or some work. And in this case, the work is going to be to split up the limit using a property of limits. The limit as n approaches infinity of 2 plus negative 1 to the n over n is the limit as n approaches infinity of 2 plus the limit as n approaches infinity of negative 1 to the n over n if both limits exist. At this point, I'll show you what I mean when I said we'll bring in the theory as we need. There is a theorem in our textbook that says that if the limit as n approaches infinity of the absolute value of a sequence a sub n is equal to 0, then the limit as n approaches infinity of the not absolute value of a sub n is also equal to 0. As a result, since the limit as n approaches infinity of 1 over n is equal to 0, we know that from first semester calculus work, it follows that the limit as n approaches infinity of negative 1 to the n over n is equal to 0. That means then, considering the sum of limits that we wrote before, the second limit is equal to 0, and so the limit as n approaches infinity of 2 plus negative 1 to the n over n is equal to 2, agreeing with our guess. Now the limit makes intuitive sense if we look at the curve, or the curve, it's not a curve, if we look at the set of dots, right? They're approaching this horizontal value of y equals 2. But that's not, again, what math is built on. It's built on definitions. We say that the limit as n approaches infinity of a sequence a sub n is equal to L, or we can write that a sub n arrow L, right, approaches L as n approaches infinity. We say that if for every epsilon greater than 0 there exists a number n, uppercase n, such that if lowercase n is greater than uppercase n, then the absolute value of a sub n minus L is less than epsilon. What does this even mean? It means if the subscript n is big enough, then the values of the sequence will be within epsilon of L for any epsilon you name. According to our picture here, what that means is that we can define an epsilon band around the limit 2, and as long as n is bigger than some number that we can identify, in this case by looking at the graph, then all of the dots are going to be contained within the epsilon band, right? The upper one would be 2 plus epsilon, the lower one would be 2 minus epsilon. And the definition of a limit means that this is true no matter how small we make the epsilon band. For any epsilon, you just have a different n, right? A different uppercase n. So does every sequence have a limit? Let's do the same things we did before with a new sequence, a sub n. And by the way, that's how we denote sequences, a sub n. And here a sub n will be equal to 1 plus 10 to the n over 9 to the n. The first 10 terms denoted curly braces, a sub n going from 1 to 10. And when we say n going from 1 to 10, what we're doing is we're going to put the numbers 1 through 10 in place of n. This is like function notation, right? Instead of writing a of n, we write a sub n to denote that it's a sequence. And using that calculator, the first 10 terms are 2.1111, 2.2347, 2.2717, 2.5242, 2.6394, 2.8817, 3.0908, 3.3231, 3.5812, and 3.8680. Here I have the 10 values plotted, and it looks like there's just a general upward trend. So the question we're answering is, does it look like this is trying to become any number in particular? And I'd say the answer is no. So I'll say that the sequence curly brace a sub n does not appear to have a limit. And the reason for that is really that the ratio here, 10 over 9, we have 10 to the n over 9 to the n. The 10 over 9 is greater than 1. And based on the graph, we would say that the entries appear to increase without bound. A little more formally, we would say the entries of curly brace a sub n appear to increase without bound. We say that this sequence is divergent. The alternative is that a sequence would be convergent, right? So our choices are convergent or divergent, and this one is divergent.